Hey everyone, welcome back. This is another one of the section 3 walkthrough sample question videos. This one, I know this one's been pretty heavily awaited. I would imagine it's been a couple of weeks since I've been able to do one. They take quite a while to get the questions put together, but I've put one together today. It's taken a little bit longer than usual, but that should mean that they're actually pretty good questions, hopefully anyway, so we'll get stuck into them. Some people did ask me as well about what app I use for the Write With Me series. I mentioned it a few times in the other videos, but I've never actually explained much. I use the Notion app. Some of you might be familiar with it, others who aren't. I would say jump onto it. I'm a huge advocate for it. Notion, if you're watching, we can always do a sponsorship. Yeah, I've turned like pretty much all of my students onto it. They all now use it. It's kind of cool. I've gone back to face-to-face shoots and they all pull their laptops up and they've all got these Notion setups and everything, and I'm always asking them like how they've got it set up. One of my youngest students is really into it since I turned him onto it, and a lot of the time he teaches me some of the little tips and tricks and that kind of thing, and he always has a really cool setup on there with calendars and stuff. So I usually learn a lot of my tricks from him actually. But anyway, so what we'll do is this one is a pretty much completely physics-based set of questions. There's some maths kind of reasoning in there as well. I know these are the things that people are probably most concerned with. It seems to be the most common complaint from people, that it's the thing that they're less familiar with, something they've maybe never studied, or just the questions that they find more difficult. Even though they only make up 20% of the entirety of the section 3 questions, or at least physics does, they do seem to be causing a lot of trouble. And so if you can kind of get these under wraps, then you should be able to tackle a fair chunk of section 3 pretty confidently, and that could significantly improve scores as well. So we'll go through them, and as always, if you've got any questions or anything, just leave me a comment below. All right, so let's get stuck into it. So here, I've already posted this up on the resources page, so I won't bother reading through it. It's pretty heavy on this one. I'm assuming you've already gone through it at this point and are looking for the solutions. So as a summary though, we're given, or I've put in information about luminous efficacy and luminous efficiency as the two. And yeah, there's a table with a bunch of different data ranges there, a graph as well, and a little bit of a formula and some constants and some numbers as well. So with question 1, it's just a dimensional analysis question. So the dimensions of luminous efficacy in terms of the standard dimensions, length, time, mass, and luminous flux J as well, is which of the following? So with these ones, you definitely want to just solve it and not do the test and check method in any way. And the way that we would do that is we would first go, all right, well, where was luminous efficacy brought in? And we can see that luminous efficacy is a measure of how well a light source produces visible light as a ratio of its luminous flux, which is mentioned in the dimensions, and its power to its power, so a ratio of the two. So a ratio means that you're dividing them. So if we do this as a ratio of flux to power, then we need to sort out power, because flux is, or luminous flux is already given as J. That is a standard dimension. So we've got J per power. And then from there, with power, we need to clean that up. So power is energy per time, right? Energy emitted per time. And so that becomes times and flip. We get JT on energy. So then energy, we need to work out. Energy can be thought of as work, or work energy. So work energy then is going to be given as force times displacement. So force times, and displacement is a length, so I'll put in that there as well. And this is where some of the formulas from physics do come in a little bit. And then force is still not a standard dimension, so we need to sort out force. Force is mass times acceleration. So now we have J times T over mass, which is a standard dimension. And then acceleration is measured in meters per square second. So that is length per square time. And then we multiply that by length. And now we have JT on ML squared on T squared. And we're dividing by a fraction. So we can times and flip that fraction over ML squared. And then we get JT cubed. And let's also do the index law at the same time. These are underneath, so these have negative powers now, m to the negative 1, L to the negative 2, and then we just match. They might be in a different order in the question, but it doesn't really matter. So J, can see J, T cubed, looking good for A, and then m to the negative 1, and then L to the negative 2, and the answer is A. So then the ratio of emitted energy to energy of visible light on the surface of the sun would be approximately. So there's a bit of information going on here. So first of all, we've got to give a ratio. Remember that ratios can be whole numbers. If they are, say, 1 to 1, then it's 1, or 7 to 1 would be represented as 7. Same thing, 14 to 1, that could have been written as 14 as well. So this is the ratio of energy emitted to energy of visible light. So it did say in the STEM that I wrote that the two different numbers that we're given are efficacy and efficiency. And you'll notice that there were definitions of those. So we can see that efficacy is the ability of it to give light, whereas efficiency actually says here it's the dimensionless ratio that is commonly misappropriated as blah, blah, blah. Luminous efficiency is measured as the percentage of energy radiating from the source that is converted to light within that visible spectrum. So if we look to the sun, we can find that just here as a class G star, and we can see that its efficiency is 13.6%, right? Now, what you got to be careful of is what the question actually said. So in it, I didn't actually go with the light visible to the total, it was the other way around. So rather than 13.6 to 100, it's 100 to 13.6%, like that. And if we simplify that, we can do it as like 100 divided by 13.6, which is basically 100 divided by 14, which is approximately 7. And so therefore we get a 7 to 1 ratio, and the only option then is going to be D. Keep in mind, you don't have to do really accurate calculations because all the ratios given are wildly different from each other. So even a ballpark, you could actually you could do 100 divided by 7 and then divide that by 2, because 7 times 2 is 14. That could be a little bit easier to do some short division. I never really learnt long division in school, and truthfully, I still don't really remember how to do it. So I just kind of avoided it at all costs. Which of the following statements are false? So the matter of the radiation source can impact luminous efficacy. That is definitely true, because we can see that the matter here, we've got tungsten light bulb versus with 2800K. There's a few different things. We've got all these other 2800K numbers as well, and they all have different efficacies. So clearly the different material is actually having some kind of an impact. So that one actually would be true, and therefore is not our answer. B, sources of radiation with greater temperatures or K values provide more energy per second. So this, I'll just kind of give away, this is the correct answer, i.e. that it's a false statement. The trick to it is that if you actually look at it too mathematically and try to overthink it, you'll probably get caught into the trap of the question. So sources of radiation with greater temperatures, K values provide more energy per second. If we look at that, the first thing is we're trying to measure the impact of just the K values. And so we want to hold all else constant. And I talk about this in a few of my other videos. So if we look, for example, we can see through here, a lot is being held constant. You can see black body, although I've put a slight typo there that I'll have to fix. 2800K, this one though is 5800K. But you can see there's also these changes in phototopic sensitivity range. So what that means is that if I just lock this for a moment, what I want to do is try to compare what's happening in the increase in K values so long as these are being held constant. So let's say I take the 5% here and I increase the K from here to here like that, and I'll look at what happens to the efficacy. And the efficacy goes up slightly, so there's a positive relationship. Now the efficacy was the lumens per watt, so that is flux per power. And so if you look at the statement, it kind of almost looks right, because we go, oh, well, energy per second, that's power, right? But it's an increase in efficacy, which is a ratio of the flux to the power. So it doesn't necessarily mean that the power is going up. If the ratio is going up, it's actually less likely that's going to be the case, but it's ambiguous. We can't tell. It's just the ratio of the flux to the power is going up, not necessarily the power. And so that is why B is actually wrong, and therefore our answer. Let's rule out the others though, because that's the method that you'd want to use. So increasing luminous efficacy causes an increase in luminous efficiency. So we can see that there is a direct correlation between them. Generally speaking, as we go down the table, we see an overall increase in efficacy, and we see an overall increase in efficiency. And you can even see that when there's large jumps here. So it's not linear in the numbers that we're given, but there may be a linear or exponential relationship between them, but it's definitely a true statement. And then radiation of wavelength 200 nanometers gives a luminous efficacy of 0. So this one here almost sounds like it could be false because it just seems too exact, and it's talking about zeros and stuff. But remember that luminous efficacy was relating only to visible light, that is within the visible spectrum, 350, 380 nanometers to 800, and 200 is below that. That would be in the infrared region, and or the ultraviolet region, I should say. And you can see here from the graph, anything below 400 pretty much is not going to get picked up in this discussion. And so therefore, that one actually would have a luminous of 0, so therefore it's not our answer. All right, moving along, then we have questions 4 and 5 on the same stem. I tried to make this a little bit bigger. Based on the information presented, a black body with 5800 K radiation truncated at 12.5% of the phototopic sensitivity range would have a luminous efficacy of approximately. Now this one is about extrapolating data, right? So there's two things, because it says based on the information. Obviously the first thing is, if I can find it, here it is here, it links pretty closely to the table. The other thing that we have to use though is the graph as well. So you can see that what this means, you don't actually have to come into the test or into these questions knowing what this really means. It's more so about relating it to the information that's given. And so the sensitivity range is going to be really the visible spectrum. And when you're talking about truncating a graph, you're talking about chopping it off, right? Chopping off sections. So we're going to be truncating it at greater than or equal to 2%. So that would be almost everything, right? Maybe just between here and here. Then we cut it to 5%, so we're kind of coming in. So as we increase that percentage there, then what's going to happen is we're slowly getting an increase, an exponential increase in the efficacy as a result of this curve here. So we can see that when we go from 2% and we want to hold everything at 5800 Kelvin, so I'm going to get rid of those things. We're talking about 5800. So we're going from 5800 to 5800, ditch that, 2% to 5% times 2.5. And then over here, it's going all the way down to here, goes from 292 to 348. If you look at the question, it's asking about 12.5%, right? And so 12.5% is 2.5 times 5%. So we've got that same pattern. So if we apply this same concept, then we should get that same ratio of change, although because of the exponential format, it should be a little bit larger. It should be growing by larger and larger increments. And so what that means is that we can start off by assuming a linear relationship and saying, well, then the ratio of 348 to 292 should be basically the same as x, which we're trying to work out, over the base 5%, which was 348. In other words, the ratio of the jump in efficacy should be the same, assuming a linear relationship. So then if we do that, we can solve for x here. We can put that over here. I'm going to call 348 350 over 292, and let's call 292 300. The reason why I can do that is because I'm rounding up on the numerator and I'm also rounding up on the denominator roughly, and the little increments of 2 and 8 relatively insignificant in the scheme of the question. So this will help me solve x assuming a linear relationship. And if I do that, I've got to do 350 squared. Now, the way that I would do that is just go 35 times 35, right? 3 times 3 is 9, but it's in the 10, so 900. 3 times 5 is 15, but again, 10 times greater, so 150. It's a perfect square, so I'm going to double that, and I get 300, and then from there, 25. You could also do it in full as 30 plus 5 and 30 plus 5, and you could use all kinds of different expansion methods. Like that is a good way to do it. And when we add all that up, we get 1225, but remember that I was completely ignoring an extra 0 from the 350, so I'm going to put both of those zeros back on, and there's my answer for that, and then it's divided by 300. So how do I do that? What I'm going to do is first pair off a couple of zeros, and now it's just 1225 divided by 3. And again, you could do the full division, or you could just kind of roughly get it, and you'll get about 400-ish, really 408, but we'll just say 400. And this is exactly why this one is here as a trap answer. So that would be on a linear relationship. If we assume it's exponential, it should be quite a bit more than that. And so the only option then would be B, 450. It would not be less, right? And it can't be 725 because if we look over here, ideal monochromatic source 555 nanometers gives an efficacy of 683 and 100% efficiency, which means you can't really go beyond the 683. And so therefore it's B for that reason. With question 5, if the sun's average visible light wavelength is 600 nanometers, the number of photons emitted by the sun in 10 seconds would be what? And we're looking at just rough calculations here. So again, you don't have to be super accurate, but this is a bit more of a maths heavy question for sure. So we're told that the energy of a photon in the stem is given as hc on lambda, and we're told that h is 6.63 by 10 to the negative 34. The speed of light is 3 by 10 to the 8. And lambda is the wavelength, which we've got here as 600 nanometers, or 600 by 10 to the negative 9, or 6 by 10 to the negative 7, like that. So we can get the energy of one of these photons, right? So if we do that, again, we're ballparking it. They're all in orders of magnitude, so I'm not going to fuss about the digits out front. That's a good shortcut. So 6.63 and 6, I'm just going to cancel them off as if they're both 6. And then from there, I get 3 by 10, and I'm going to use index laws. Negative 34 plus 8 is going to be negative 26, and then take away a negative 7 is going to be negative 19. And that's how many joules one of those photons is worth. The next thing then is we're told the power rating of the sun. And we're told that the sun is, over here, 3.9 by 10 to the 20 megawatts, right? Megawatts being 10 to the 6. So what that really means is in watts, that's 3.9 by 10 to the 26 watts. And so we bring that down as well. So it's pretty unlikely that you get a question like this. This is probably a little bit too maths heavy. But if the power is 3.9 by 10 to the 26 joules per second, right? Now we're doing this for 10 seconds. So if we want the energy, we take the power and we times it by the time to cancel that out. So times that by 10, and then we're going to divide that by the energy of one photon, and that will tell us the number of photons that must be getting emitted in that 10 seconds. So we can see again the digits out the front. 3.9 divided by 3 is 1.3, and then exponentially here we've got 10 to the 26 times 10, it's 10 to the 27, and then take away a negative 19 is then going to give us 46. And so, because it's greater than 1 by 10 to the 46, it's a little bit higher. So it's somewhere between 10 to the 46 and 10 to the 47, like that. There we go. All right. So then unit 2, so this one, looking at some forces and torque as well, because I've noticed that one's come up as a bit of a problem for some people. So a folding table of length L, mass M is designed such that when it folds down, it's supported by the axle attached at one end, and a fixed and a supporting beam that the table rests on at its free end when folded down. When folded down, the table has a vase of mass X kilos placed 0.6 L from its free end. When being folded up or down, the angle between the tabletop and the horizontal is given by theta. So that is going to go just here when it's being folded up or down like this. Sine theta is going to be alpha, cosine theta is going to be beta, and assume that the value of gravity is 10. They'll pretty much always do that. So the force exerted by the supporting beam is. So with this one, whenever you have anything to do with supports, the amount of force or the amount of weight force that is pushing down on either end is going to be proportional to the distance that it is from the other end. So what that means is the axle, although fixed, is actually bearing some weight as well. And we've also got to consider the center of gravity of the table. So the center of gravity of the table will be at pulling down here with a weight of mass times gravity, which is 10. So that is 10 m, because the mass of the table is m. So we've got that force pulling down, and that is at a distance of 0.5 L from the support beam. Then the vase, which is sitting here, is pushing down with a weight of x and then times gravity, so 10 times x, like that. Now, the important thing is the amount of force that pushes down on support beam, on the support beam, is going to be proportional to the distance it is away from the other end. Reason being is, if it's further away from the support beam, then it's going to be pushing down with less force. If it's closer, it's actually going to be pushing down with more force. So what that means is that you've actually got 0.4L to the other end. We're going to use this number to help us out with the amount of force pushing down over here. And likewise, to the center, we've got 0.5L, but I won't label that in because it's getting a bit crowded. So what that means is that the force that's actually pushing down on support beam B, or the amount of force that support beam B is actually pushing up with, has to counteract the force that is pushing down on that support there. So the amount of force pushing down is going to be 0.5 of the weight of the table, so 0.5 times 10m, and then plus, it's also got the weight of the vase, and the vase is 10x at a distance of 0.4 of L. So plus, and then that would be 0.4 lots of, or 40% of its mass. And so that gives us there 5m plus, and there's here 4x. And so then the answer is B in that case. Question 2, if a second identical vase is precariously stacked on top of the first one, then the increase in force applied by the supporting beam is, and you can see there's a mix of questions or answers with percentages, and then one that's in newtons as well. So it could be any of them. So what we have to do first is go, well, what is the increase? Because that's what we're trying to focus on, not the actual final mass or the final weight. So the increase is going to be another vase, which adds a weight of 10x, like that. And so if we look at that, how much of an increase then is actually being added to support beam B? Well, not all of the 10x, only 40% of it again. So times that by 0.4, which gives us 4x. That's how much is being added. So there's nothing there that says an increase of 4x newtons. So already I now know that one must be out. Then the next thing is, well, what if it is as a percentage? So that, as a proportion of what it was, it used to be 5m plus 4x, right? And then to turn it into a percentage, we times that by 100. And if we do that, we just times it to the top. It gives us 400x over 5m plus 4x percent. And so therefore, the answer is B again. I seem to like B with the answers. Then question 3, if the table is lifted from its center with an upward push, so the tabletop slides over the hand, the torque required to lift the table is given by. Now this one I'm just kind of messing with the wording of it to explain it. So the idea is, I'll try to explain it with the pen here, is it's kind of like if this is the tabletop and you're pushing up in the middle, you're keeping your hand in the middle, and then you're letting the table just kind of slide over your hand as it raises, right? So you're not actually moving your hand left or right, you're actually just moving it vertically up, and the table is then sliding over as it bends upwards. So what that actually means then is that the radius, which needs to be perpendicular, is actually not changing, right? So you're always pushing at the center. When it was lying down flat, that would mean that you're pushing right at the center of mass. Therefore, the radius of torque is going to be 0.5L, half the length, right? And even though the table will be sliding, you won't be changing that perpendicular radius. The force that you'll have to be overcoming is still going to be the gravitational force of the table. And the gravitational force of the table is going to be, where are we? Mass times gravity. So 10m, right? So that's the force that you need to apply, like that. And then to get torque is force times radius. So that is 10m multiplied by 0.5L. And that gives us 5mL. And I just kind of did that because I thought it was funny because it kind of looks like mils. But anyway, it's B yet again. Then question 4, an alternative method of raising the table is to hold firmly onto the middle of the table top and push upwards and arc your hand until it is in the upright position. So really that just means like grabbing the table and twisting like that, but holding onto the table the whole time, not letting it slide. in any way. And so what that means is now the perpendicular radius is actually the table itself. So you're kind of grabbing it in the middle, and then as you're twisting it, your hand follows it and is still holding it in the middle. I'll just make that actually the middle, like that. And that means that the force that you're applying is always perpendicular to the tabletop at any given point, like that. So what that means is your radius is here and now it's here, which means that it'll always stay as 0.5. It'll never actually change. And so you're moving your hand with it. So as you do that, what that then means is that the force that is actually working against you is decreasing, because you're no longer working directly against gravity. So what that means is that you have force of gravity pushing straight down. And then from there, you would have the force that you apply, which we can pull down to here. And this line here, you always want a right angle triangle. And then the trigonometry would say that the angle theta, which is here, is also here in this little triangle here. And so this is actually 10m. And this here is the force that you're actually applying. And we can work that out. So if I just kind of redraw that triangle a little bit more neatly, like this. So this is 10m and theta's over here. This here would be the adjacent, making this the cosine, right? And so it would be 10m times cosine of theta. And we're told in the question that cosine of theta is beta. So that is 10m beta, like that. That is the force that you're actually applying at any given point as it twists, because theta is a variable. And then from there, that means that the torque that you apply is going to be force times the radius, and we just proved the radius is going to stay as half L the entire time. So that is 10m beta times by 0.5 L, and then the 0.5 and the 10 gives us 5m beta L, and so therefore 5 beta ml. And that one is A. And then finally, compared to the first method of sliding the table over the hand, gripping the center of the tabletop allows for. So we've kind of already answered this one in the previous consideration. A decrease in force required as the table is lifted. That would be absolutely true, because you're no longer always working against gravity. At the start, you're working directly against it, but then as you're twisting it, you're actually working obliquely against it, and therefore you're getting less and less force. You can also think of this, just think about if you were to actually be twisting that tabletop, it's going to be easier at the top to push it, because most of the work now is being pushed horizontally, and you're no longer working directly against gravity. But it would definitely not require an increase in force, and then it wouldn't require, so a decrease in torque applied as well. So in that one there, because the radius is staying the same, the force, actually, you know what? I need to change that. I'm just going to throw that in and leave that as two answers as a bit of a trap, I guess. A decrease in torque applied to the table. So if the force is decreasing over time, then what that would actually mean is that the torque would also be decreasing because the radius is staying constant. So that would also be true. And then, so I'll accept A or C, error in the question. A constant force required to lift the table? Absolutely not. We can see that as we go up, the force required is going to be less and less each particular time. Cool. And notice it does say required. Yes, you could hold or apply a constant force, but it's the requirement is not going to stay constant the entire time. And there we go. So let me know what you thought of them. Excuse the error in question 5. Anyway, I will leave that one there, and these are all up on the resources page if you haven't already seen them. And let me know what else you'd like to see. I think at this point now, I've done so many of these kind of walkthrough videos, it's better just to kind of theme them now and look at specific elements of section 3 to help people out. So if that's something that you'd like to see, just let me know what you want to see, and then we'll put another one together. Otherwise, guys, I will see you guys in the next one.